So the first talk will be by Yiding Feng and is on batching and optimal multi-stage bipartite allocations. And Yiding, you can get started.
Okay, thank you, Matt. So today I'm happy to talk about my joint work with Red from Chicago. So this project is basically motivated by the real-world application in the online market, where the platform needs to dynamically match the demand request to the supply. And within all those applications, different applications have different allowance for the latency. In other words, the longest waiting time a demand request can wait before it has to be responded. And in the application which allows some of the latency, the platform can make the more efficient matching decision by using the batching strategy. Specifically, it will group the demand requests together in batches and then makes the stage-wise matching decision, one for each batch. It's easy to imagine that in this new paradigm where the platform using the batching strategy, the matching efficiency will be improved. So a question could be asked here is that, can we theoretically measure this efficiency improvement by using this batching strategy? And to do so, we need a theoretical model for this one. And before that, let's first revisit the classic model of online bipartite allocation. So in online bipartite allocation, there are different variations. For example, online bipartite matching, online bipartite packing, and some other variation. So in today's talk, we will mainly focus on the vertex weight B matching and say how can we modify it to capture our new paradigm where the platform can use the batching strategy. So in an instance of vertex weight B matching, it will be given as a bipartite graph, where on one side we will have a supply node, which will be given in an offline fashion, where every supply node will have a heterogeneous weight, as well as a capacity, which captures the total number of demand requests it can be matched with. And on the other side, we'll have a demand node, which will arrive to the algorithm in an online fashion. And once the demand nodes arrive, the matching algorithm needs to make the matching decision for that node immediately. And in this talk, we will mainly focus on how to modify this model to capture in our new paradigm. And additionally, we will assume that the matching algorithm can produce the fractional solution. And we will assume that all capacity for the supply node will equal to 1. Cool. So far, the model assumes that the demand nodes will arrive one by one in an online fashion. And in our new paradigm, we will assume that they will arrive in batches. Specifically, suppose we are fixed that there will be K stage, and therefore, a new batch of demand nodes will arrive in each stage. And for example, here is the instance of 2 stage, and therefore we will have 2 batches. And another instance of 4 stage, and therefore we will have 4 batches. And in our model, we do not have any assumption about so the number of demand nodes within each batch. Cool. Now let me formally define the class of matching algorithm we are considering. So once a batch arrives, the matching algorithm will observe the demand vertices within this batch, as well as the incident edges. And then this algorithm needs to make a irrevocable matching decision, which will be a fractional matching between those demand vertices and the supply nodes. And here the Yj corresponds to the current consumption of this supply nodes. In other words, it will be the fractional degree has been matched in the previous stage. And our goal is to maximize the weight of the matching, and we are competing with an in hindsight solution. In other words, optimal offline. And in this paper, we'll try to identify the optimal competitive ratio if we fix the number of stage, capital K. And let me remind you that if capital K equals to 1, we will only have a single batch. So this will correspond to the fully offline problem. And therefore, we know gamma 1 will equals to 1. And in another extreme, where every batch contains a single demand vertices, this will correspond to the fully online problem. And in this paper, our formal research question is that in the middle ground region, where we have capital K batch, can we identify the optimal competitive ratio? And even though our model assumes that demand nodes arrive in batches, but we can always pretend that they are actually arrive in an online fashion. And therefore, the literature from the online bipartite allocation with vertex arrival tells us greedy allocation will always be half competitive, and balanced algorithm will be 1 minus 1 over E competitive. And in this paper, we identify the optimal competitive if I fix the number of stage K. And let me remind you that this gamma K will be between 1 minus 1 over E and 1. For 2 stage, it will be 3 over 4. And for 3 stage, it will be 90 over 27. And as capital K goes to infinite, it will convert to 1 minus 1 over E. And we also show the same results hold for other variation of this model for both fractional solution and integral solution with large budget assumption. Now, let me give you some taste of our technique toward this result. So in this paper, we introduce the so-called polynomial regularized convex programming matching, and it will contain 3 steps. So in the first step, we will try to identify a sequence of polynomial with decreasing degrees, 1 for each batch. And once a batch arrives, we will try to write down a regularized max weight matching convex program, where in the objective function, we will use those polynomial we identify in the first step as a regularizer. And the solution of those convex program will be a fractional solution we assign at that stage. And at the end, to show that this algorithm attains the optimal competitive ratio, we will consider the KKT condition of those convex program. And those KKT condition will induce a graph decomposition, which we will use to build up a primal dual analysis. And specifically, for the dual assignment we construct in those analyses, we'll be using the property of our graph decomposition. In other words, they will be inspired by the KKT condition of our convex program. And in this sense, the convex program we study in this paper provide a new interpretation for the classic primal dual analysis in the classic online bipartite allocation with vertex arrival. Specifically, for the dual assignment in those analyses, it can be solved as a consequence of the KKT condition of our convex program with some specific regularizer. And for example, for the balance algorithm, which attains 1 minus 1 over E approximation, its dual assignment can be solved as using our convex program. And instead of using the regularizer using the polynomial, but using the exponential function as a regularizer. And that's all of my talk. So if you have any question, please feel free to ask a question. And you can also connect me through my email. Thank you.
Thanks, Yiding. So we can take one quick question if someone has one while Clay, if you want to start sharing your screen. And if there's not one from the audience, Yiding, can I quickly ask? You mentioned that for the integral setting, you needed a large budget assumption. Do you believe that that's because you would need a more complicated algorithm to work with a budget of 1, or you believe that the algorithm, or you believe that there may be a stronger impossibility result? Yes,
I think this is a very good question. So first, the large budget assumption is the standard assumption for this kind of online matching literature. And on the other side, we also conjecture that the same competitive ratio can be achieved for the integral setting with capacity equals to 1. But certainly our current algorithm does not work, and we need to think about if there are some other ideas.
Cool. All right. Thank you very much. And we'll move on to the next speaker, who is Clayton Thomas, who will tell us about tiered random matching markets.
Thanks, Matt. And this is based on joint work with Itai Ashlagi, Mark Braverman, Amin Saberi, and Geng Zhao. So this is a paper about the stable matching problem. By a standard analogy, this is seeking to match n men to n women, when each agent has preferences over all of the agents on the other side of the market. And our goal is stability, and this is the property that once I output this one-to-one matching, nobody wants to get up from their assigned partner and match with each other instead. This is used, heavily studied in theory and used in practice, and it's been argued to be really crucial to prevent market unraveling. I can tell agents when I give them this matching, why would you want to deviate from the matching? Nobody would want to do that with you. And it's used to match students to schools and residents to hospitals, as well as other things. The most common matching to use is the one-side optimal matching, which can always be found by the deferred acceptance or Gale-Shapley algorithm. As a reminder, this proceeds by the men proposing down their preference lists from their favorite to their least favorite, and the women tentatively accept the best proposal, reject all others, and they continue making these proposals. To study these markets, you kind of need to put distributions on the preferences of the agents. This really gives a lot of valuable insights that you'd miss by just doing deterministic studies. And to give us a baseline, one of these insights is that with in men, in women, and uniformly random complete preferences over the other side, the men are at a very large advantage. They get their log nth favorite woman in expectation, where women get much higher, much further down their lists and divided by log n. We call this place that the agents get the rank that they achieve. And a long line of work has extended this analysis and found a variety of different interesting models that show that different market parameters can have profound influences on these ranks, and that a lot of interesting things happen. But up until now, not much has been known, at least not in detail, for cases where the agents are non-uniform. Most of the tools were really specialized to this indistinguishable agents case. So in this work, we want to give agents some a priori quality before the market starts. There are some good and some bad agents that are less desirable. And what we'll be interested in is these rank statistics, how much agents like their matches, and we'll be interested in who ends up matched to who. So the distribution we study over preferences is a tiered matching market. This has a constant number of tiers for the men and for the women, with a constant fraction belonging to each tier. And there's these constant public scores, or you can think of it as the weight that the agents have attached to each tier. If this is a residence matching to hospitals example, maybe the tiers on the residents are the A students for medical school, the B students, etc. And the way preferences are drawn is from favorite to least favorite by sampling proportional to the score of the agents on the other side. So for one example, a woman W is the favorite of each man, with probability her score divided by the sum of all of the scores of the women. And for one more example, if W1 and W2 have score 9 and 1, then 90% of men will rank W1 above W2. We think this is a really natural next step beyond uniform markets. In fact, it's a special case of a pretty well-studied set of preferences called popularity preferences, which think of these scores as the popularity of the agents. The only additional structure we have is these tiers, big blocks of agents with the same score. But the key assumptions that the analysis uses are that the preferences are identically distributed for each man, and that these weights are constant. There's only constant variation in quality. Okay, so diving into the results. For the purposes of this talk, I'll phrase the results where only the women are in the tiers, and then when only the men are in tiers. So these expressions end up giving the rank that agents on both sides of the market end up achieving. The first thing we can notice is that up to constant factors, this matches the uniform setting. But the total number of proposals has increased by this factor, which depends on the smallest public score on the women's side, alpha min. This factor is the ratio of the average score, this dot product of the score fractions and the weights. And this is pretty natural because the bottom tier of women is a real bottleneck in this market. Men don't want to match there. And so they'll keep making proposals until finally that bottom tier is sort of matched. For women, the higher your score is, the lower your rank is, and this is in fact directly inversely proportional to the score. This makes sense. Better agents get better matches. And something really interesting to note is that the distribution or the tier proportions just factor out. They don't end up mattering for the women. They can sort of just think about their absolute quality above some baseline alpha min. When the men are organized into tiers, the ranks end up being given by this expression. These are all in expectation. And again, this matches the uniform market up to constants. And again, ranks are inversely proportional to score. But here, men have to worry about a little more. Their tier setup, the tier fractions delta, do factor into their type. And they sort of have to worry about the ratio of their score to the average, or more precisely, the ratio of their inverse score. Proving that these men's ranks is inversely proportional to their score ends up being like the technical crux of our paper. So just for some very brief intuition, the reason it comes out of the model is that it's sort of the case that increasing your score directly corresponds to increasing the probability that your proposals are accepted, and thus inversely corresponds to the number of proposals you need to make throughout the matching market. It turns out that when you put agents on both sides, these results still work together, and both men and women make a number of proposals which is proportional to their score. And this ends up having a really interesting consequence on what we call the distribution of match types. This is the expected fraction of matches in the output, which are between tier J of men and tier I of women. And we consider this for each I and each J. It ends up being the case that these fractions match what you would see from a uniformly random matching up to lower order terms. And this indicates that there's no sorting in this market. And instead, agents have to settle for things they idiosyncratically like and not things they like because of the tier structure. High types don't necessarily get high types. And just for a super short sketch of why this happens, in this market with just two equal sized tiers of scores 2 and 1, each woman receives twice as many proposals from the low tier men, but she weights the proposals from the high tier men twice as much. So in the end, it's 50-50 whether her favorite is from the high tier or the low tier. So for future directions, we would like to extend the model, say, to private scores instead of public scores. Things get a little more interesting when there are a lot more agents on one side. And we think a lot of these techniques or intuitions can be applied to mechanism design, but that's, of course, for future work. All right, thanks.
Thank you. So I think we fell a teeny bit behind time. So maybe can Hedyeh share your screen, and if you have questions for Clay, we have the long period after all the talks are done, or you can ask in the Q&A right now. All right. And the next talk will be on randomness and fairness in two-sided matchings, and it'll be given by Hedyeh Beyhaghi.
Thanks, Matt. This is a joint work with Ava Tardos. So in this paper, we study matching markets where both sides of the matching have limitations. On the one side, we have the applicants that, although find a lot of the job positions on the other side desirable, they can only apply to a limited number of them. This may be because the system has imposed this limit or because preparing the applications is time-consuming and costly. On the other side, we have the job positions that need to run an interview process before hiring their applicants, and they can only interview a limited number of their applicants. Our goal in this paper is to study the effect of these limitations on the matching, and more particularly the size of the matching. Traditionally, the matching algorithms did not take these limitations into consideration. For example, the deferred acceptance algorithm by Gale and Shapley assumes that the participants can consider as many options as they want. In the more recent years, there have been more work on matching with limitations, But as you see, there's still very few studies on limitations on both sides. Let me define our model more formally. We have n applicants and n positions. We show the applicants by circles and the positions by squares. We focus on the case that the preferences come independently from uniform distribution that Clay also mentioned in his talk. So this simple case lets us make our analysis more tractable. And also we see interesting facts even in this simple case. We run a 3-stage matching mechanism. In the first stage, each applicant applies to k positions. Here, k equals 2, so each applicant is applying to 2 positions. Right next to each position, we show the applications they have received. In the second stage, the positions accept k prime of their applications for interview and reject the rest. Here, k prime is also equal to 2. The positions are accepting 2 of their applications and rejecting the rest immediately. After they run the interviews and refine their preferences, we run the applicant proposing deferred acceptance algorithm. And finally, we consider a large market setting, meaning that we study the market when k and k prime, the limits are constant, while n approaches infinity. And the main problem we focus on from here on is to find the expected size of the matching or fraction of matched participants as a function of k and k prime, the limit on the number of applications and interviews. Okay, so let's start with the case where the limit on the number of interviews is 1. We show that in this case, when n approaches infinity, the fraction of matched participants comes from this formula. The proof of this is not too complicated, but we won't get through that in this talk. Instead, I want to draw your attention to something more important, which is the shape of this function. Okay, so here on the x-axis, we have k, the number of applications, and the y-axis is the matching size or fraction of matched agents. So as you see with one application, around 63% of the participants are matched. It increases with 2 applications and 3 applications to around 68%. But after that, with more applications, the matching size decreases. And this is actually the first interesting fact that we observe in this case. So based on the formula, we know that the matching size is not monotone in the number of the applications. But intuitively, what is the main reason? We realize that having more applications has both a positive and a negative effect. The positive effect is that with more applications, the number of positions that receive any application increases. For example, with one application, only 63% of positions receive any applications. As you see, it goes up pretty quickly with more applications. But the negative effect is that since the applicants are applying to multiple applications, the probability that an accepted application belongs to some applicant who has other accepted application increases. So this leaves some of the agents with more than 1 offers, while the rest receive no offer. So in this picture, we see that after we increase the number of applications from 3, the negative effect takes over and we have a decreasing curve. Okay. So we completely understand what happens when the number of interviews is 1 and all the applicants are applying to the same number of positions. But is there any hope of achieving this larger matching if we allow applicants to apply to a different number of positions? So first, we show that given any average number of applications x, it is best to let a group of people apply to floor x number of positions and the rest apply to ceiling x. Basically, the largest size of matching happens when either all the applicants are applying to the same number or they apply to 2 consecutive numbers. Based on this lemma, we can find the size of the matching also in this case. Again, I won't go through the proof, but want to draw your attention to the shape of this new function that we have. All right. So on the x-axis, we have the average number of applications by each applicant. And on the y-axis, we have the size of the matching. And for example, if we're at point 1.5, it means that half of the applicants are applying to 1 position and the other half are applying to 2 positions. So here we see our second interesting fact, which is this U-shape between two integers, meaning that the local maxima of this figure happens when all the applicants are applying to the same number of positions. So I want to wrap up the case with a single interview with two messages. The first one is that the optimal number of applications is 3, no matter what distribution we choose to distribute the applications. And the second one is that a fair system of distribution gives the highest matching size, which means that the local maxima of the figure are the integer points. And more particularly, for example, if we are here, if everybody is applying to 2 positions, if we favor a group of people and let them apply to 1 more position, or if we discriminate against a group and let them apply to 1 less position, the size of the matching is going to decrease. Okay. I also want to quickly mention what happens when we have multiple number of interviews. So the formula and the solution for this case is going to be more complicated. But at the end of the day, we are able to find the expected matching size with arbitrary k number of applications and k prime number of positions. Here, the x-axis is again the average number of applications, and the y-axis is the size of the matching. Here we see the curve with a single interview that we saw previously. This is with 2 interviews, 3 interviews, and so on. So as you see with more applications, we still have our 2 weird properties, the non-monotonicity and also the U-shaped between integers as before, but it happens with a lesser degree. I also want to quickly emphasize that these weird behaviors are consequences of limiting the number of interviews. If we don't have any limit on the number of interviews, the matching size is going to be monotonically increasing in the number of applications. Okay, let me conclude. Our main technical contributions are 1, computing the expected size of the matching as the outcome of the deferred acceptance algorithm when there are limits on the number of applications and interviews. And 2, finding the optimal way of distributing the applications when we're given the total number of applications. Our work comes with 2 policy recommendations. The first one is that if we have limited ability granting interviews, we may need to limit the number of applications as well to have a large matching. And the second one is that the optimal matching size is achieved by a fair system. That's all. Thank you for your attention.
Awesome. Thanks. So I think let's go ahead with the last talk of the session, and then we can have the discussion afterwards. So I think that's
me.
Yes. Do you want to start sharing your slides?
Okay. Sorry. You see them?
No. It says you're screen sharing, but I just see a blank page.
This happened.
So this has happened a little bit. It might help if you, instead of sharing the application, just share your entire desktop.
No.
No? Well, clean it up and then give it a go.
Can you see it now?
Still no.
Okay. What happened here? Sorry.
So now we do see your desktop, I think.
Okay, can you see the slides now?
I don't think that's what we're looking at. I think we see a browser.
Can you switch to your slides?
Sorry?
Can you switch to your slides?
I have switched my screen is showing my slides.
So our view of your screen looks like it's showing a browser of a YouTube video.
Okay, that's this one. Okay, I'll cut it. I will just purge it, and I will start share screen and here, this is what I want to share. Good, excellent. Now you should have it.
Now we see it.
Good. Okay. So welcome everybody to this talk. And I hope you can hear me. This is joint work with Mihalis Yannakakis. And what it is about is the computational complexity of this fabulous scheme of Hylland-Zeckhauser, two economists from Harvard. Actually, Zeckhauser was the advisor of Hylland, who was a student at Harvard. Zeckhauser is still at Harvard. Hylland is somewhere in Scandinavia. And Zeckhauser is a very important economist. Okay, and this is for one-sided matching market. So I know this is a very diverse crowd, so let me just say what a matching market is. So these are different from commodity markets in that, say for instance, college admission is a matching market. And the interesting thing to see here is that a student cannot buy admission to UC Irvine, no matter what she's willing to pay. She also needs to be chosen. That's talking about UC Irvine. At USC, some people have bought admission. Some rich and famous people bought admissions for their daughters, and then they had to go to jail. Okay, so that's what this market is about. It's a market in which you cannot simply choose what you want. You also have to be chosen. And typically there's no exchange of money involved. So the big question is, why is this even a market as we know markets? And the reason that actually Al Roth gave me was that because it aggregates information held by the participants, which is what markets do. That's why these things are called markets. And by now there are lots of markets from all walks of life. And the best way I know how to classify them is through revolutions in computer science. The first one was, of course, the Gale-Shapley stable matching market, stable matching paper, which led to the matching of residents to hospitals. And in the so this is a very ancient field in that sense, matching students to schools, kidney exchange, and so on. And then what happened was these computer science revolutions of the internet, which gave rise to the AdWords market, which almost entirely funds Google's massive expenses, their free search, Gmail, YouTube, everything. Upwork, which matches workers to jobs. Mechanical Turk is similar. Match.com does the traditional matching of men and women. And then came mobile computing, which led to even more interesting matching markets. More interesting or not, but more matching markets, newer matching markets. Uber and Lyft, Airbnb. And there's one more matching market that's really relevant to all of us, which is not in this because it's not really mechanized like these ones. And that is the academic job market, where every hire is a one-off and you cannot really automate this process. Okay, so but that the fact that the job market has been a market in everybody's minds should tell you that this is not an anomaly to call it a market, these kinds of things. Okay, so this general and very powerful algorithmic tool. Okay, so here you can see that on the one hand, the field is ancient. On the other hand, it's in its infancy, because with these new revolutions, you certainly gave rise to very, very interesting, very, very impactful markets, which are occupying a bigger and bigger fraction of the economy. This is only a small sampling of these. So what we need really is these kinds of general tools, because if there's a new market tomorrow, you want to take one of these tools and off the shelf, just plug in a mechanism to start running it instead of devising yet another algorithm for it. And this goes back to 1979, Hylland-Zeckhauser, and they used the power of a pricing mechanism to run a one-sided matching market. Now, what's a pricing mechanism? Where you basically find prices through demand and supply, and that's you try to make a parity between demand and supply And that gives rise to many, many nice properties, has always been the central tenet in economics. It avoids artificial scarcity, has led to efficiency, has created massive wealth in the West, and so on and so forth. So how exactly it comes about will be the next slide. But what's the one-sided matching market? So you saw two-sided matching markets in the last few talks. One-sided is where only one side has preferences, unlike say the boy-girl markets where boys and girls both have, men and women both have preferences. So like agents and goods are done; they don't have preferences. Okay, and I just want to say that the Hylland-Zeckhauser scheme seems like a novelty in theory and theoretical computer science. In another theory, namely economic theory, it's a classic. So there's a new book coming out on matching markets. This Hylland-Zeckhauser will be in the very introductory chapter of that. So, so you can view this market as a marriage between linear Fisher market, which really is a market with money and goods, and goes about finding equilibria and is run through the pricing mechanism, and perfect matching. Okay, so think of the market as having n agents and n indivisible goods, and each agent has told us her utility for all the goods, uij for good j, that's for agent I, and we want to find a perfect matching of agents and goods, so that the allocation is Pareto optimal, which means that the only way to improve any one agent's allocation is to diminish another one's agent allocation. So it's sort of maximally good. Yeah, of course, if you give, okay, yeah, there are trivial solutions to Pareto optimality, but it's also envy-free and all that, so that you don't boil down to some trivial solution like. In this case, you cannot do that. But if you give all the goods to one agent, you'd say, "Oh, it's Pareto optimal." Of course, it's Pareto optimal. But that's not what we are looking for. Anyway, it's also incentive compatible in the large. So if you have lots of agents, no one person can cheat. And all these two properties really come about from the fact that we are running it through supply and demand like a pricing mechanism. And so let's talk about that. So in order to really be a Fisher market, goods have to become divisible, and that's done by making each good be 1 unit of probability shares. And you assume that each agent has $1 of money. This is fake money. It's no novelty today, but in 1979, this was a big concept to have fake money. And each good J has a price, non-negative. Okay. And the allocation now will be 1 unit of probability shares to each agent, so that the entire allocation is a fractional perfect matching, because you will have at each buyer the Xij's adding up to exactly 1, at each good also the Xij's adding up to exactly 1. And these are fractions, these are probability shares. So each good is 1 unit of probability share, each buyer gets 1 unit of probability share. So you need to find such a fractional perfect matching through this pricing mechanism. And so going further, we define the notion of an equilibrium. So given prices P, so an allocation, so always think of an allocation as a fractional perfect matching. So prices and allocation are an equilibrium if every agent gets a utility maximizing bundle of goods. So every agent solves this linear program, subject to the fact, of course, that X is a fractional perfect matching. Okay, and one small point to be mentioned, which is what leads to Pareto optimality, is that notice that an agent need not spend her entire dollar. She may be able to, her utility maximizing bundle may cost $0 for all we know. So that's what she'll get. But if there are several of these that cost less than $1 and are utility maximizing, then she should get the minimum cost. And only then we can prove that the entire allocation is Pareto optimal. This is a very subtle point, but very key to make sure that Pareto optimality holds for the entire allocation. And if you have worked on equilibria, you always have to put in the condition that the market clears, but that's guaranteed. If X is a fractional perfect matching, of course, all goods are sold because every good is 1 unit of probability shares and it's all sold by definition of fractional perfect matching. And once you get this fractional perfect matching, you apply a Birkhoff-von Neumann theorem to round it up to an integral perfect matching, and that'll also be Pareto optimal. That's very easy to see. Okay, and the point is, it is a very non-trivial, well, not very, but quite a non-trivial proof. There are more non-trivial proofs around this fact that equilibrium exists, and it uses the Kakutani fixed point theorem, which of course is highly non-constructive. So the question of efficient computability is front and center, and somehow it has not been addressed in our community. And the major hurdle here is that the market does not satisfy weak gross substitutability. What is that? That says that if you increase the price of one good, the demand of another good cannot come down. Okay, it should not. Normally, if you increase the price of one good, then other goods look better and their demand should only go up. Yeah, you have a question, Matt?
I was just giving you a heads up that time is out. So if you can try and wrap up in a minute or so, that would be good.
Lord, I haven't even started. Okay. So you don't have, okay. So anyway, for the 0-1 case, we can give a polynomial time algorithm. It goes also for, okay. And here's an example with irrational equilibria, 4 agents, 4 goods. And the amazing thing is that this example satisfies all these equations, which would tell you that it's rational because at each buyer, each good and each agent spends exactly $1. How on earth are these irrationals adding up to ones everywhere? Okay, the consequences are it's not in PPAD, and we show that it's in fixed P by giving another proof of existence of equilibrium using Brouwer's fixed-point theorem. And fixed P is much, much harder than PPAD probably. Of course, we have to show P not equal to NP to make that probably go away. And approximate equilibrium is in PPAD, where notion of approximation is appropriate to this proof. And the proof is to change the other proof a little bit. And how do you get hardness results? How do you efficiently compute equilibria, approximate equilibria? What do you do about 3-valued utilities? Because for 2-valued, it's rational and NP, 4-valued irrational, 3-valued we don't know. And there are many, many generalizations waiting to be handled, like two-sided matching markets in this framework. But nobody wants to go anywhere near because nothing can be even done about a one-sided matching market. And if I have only 1 more second, then I'll just leave you with this very important number. Thank you.
All right, thank you. So we'll transition to the discussion part of the session now. So what we can start with is if anyone has any questions from the audience they'd like to ask to any of the speakers. I think someone can correct me if I'm wrong. I think it's okay if you're a panelist already and you want to just unmute yourself and ask that's okay. And maybe
if nobody has a question, I just want to ask somebody if they have guessed what 132 is.
I think we need your help.
That's the sum of the ages of the 2 authors.
What's the
so it looks like there was someone in the audience who raised their hand. I think I didn't. It looked. Let me see. I think you can talk now.
Yep. Can you hear me?
Yes.
Cool. So I had a query with respect to the last author's presentation. So what's the empirical evidence that you have supporting your complexity? I mean, because it's one-sided matching markets. So I was thinking more in terms of the implementational, the empirical implementation, and what was the data structures that you used, if any, to.
No. We don't know that it's hard yet. No, we haven't proven hardness results.
Okay.
It just okay. I don't know. I don't want to take a crack at that kind of a question without solid evidence. But we really, I mean, all these years went into trying that.
Okay. Yeah, because the theoretical bounds look good, but yeah, empirically.
No, there's no theoretical bound. We're just saying that it's fixed. It lies in fixed P, and fixed P is fixed P complete problems are likely to be very close to P space complete problems, not close to P. So the theoretical results are not pointing to anything very useful here.
Okay.
The only
Got it.
theoretical
Thanks.
result pointing to useful is when you have 0, 1 utilities and extended to when everybody's utilities are bivalued. Everybody has 2 numbers, and all the utilities come from those 2 numbers, but the 2 numbers can be different for different agents.
Thanks.
As soon as we have 3 numbers, we raise our hands and we cannot say anything about it. For 4 numbers, we have irrational example, and that's the reason that the problem is not even in PPAD, because every problem in PPAD has to have rational solutions. And this example has only an irrational solution and no rational solutions, even though all those equations that I showed you must hold for, do hold, even for that irrational solution.
Thanks. Vijay, can you also turn off your screen share for the rest of the discussion?
Oh, good. I thought everybody wanted to stare at the number a bit more. Okay.
So I have a few questions, but people in the audience should feel free to interrupt me with questions of their own too. So can I get back to Clay? So in your model, you said that all the results held when each tier constituted a fixed fraction of the market. And I'm wondering how sensitive the results are to that assumption, or if some sense of them would hold if everyone had an individual score, or what would you expect those results to look like instead?
So in that respect, the tiers are mostly for like cleanness and convenience. The key results that it's proportional to your public score would actually still hold. But we couldn't write down what those ranks would actually be.
Got it. Thanks. And then I had a question for Hedyeh too. So at the end of your talk, you mentioned some policy implications for the work. And I was just wondering, this may be an open-ended question, but I guess sort of like how literally would you take those recommendations? Or if you wouldn't take them super literally, what's the next step that you would want to see in this line of research?
Right. So the assumption that the distributions come from uniform distribution is essential for our results, but it's mainly essential because of the technical reasons. So like we can only calculate our findings when the distributions are uniform. So it depends on how much still the same weird behaviors hold with non-uniform distributions. So I think like maybe that's the first step to make the model more realistic. But I just want to mention that we kind of understand study the role of the randomness. And there are other papers that study kind of the extreme case when the preferences are almost identical or very correlated. So in that case, the congestion is mainly like the non-monotonicity, or the congestion is mainly because of popular agents. And here we get the opposite case. So it depends on how much, when we look at the models in between, the things hold.
So
Thanks.
wait, sorry. Are you saying like the findings reverse in the really correlated model?
If you get the congestion, it's mainly because, for example, let's say that some people are much more popular than the rest.
Yeah.
So they will get like a lot of offers, right? So like in that case, it's not too surprising to see that with more applications, your matching side may decrease.
Right.
And then I have maybe one follow-up question that's maybe appropriate for either Hedyeh or Clay. So I guess Clay's paper involved a model that was kind of like barely beyond uniform. Do you have any sense of if someone were to push in a next direction, if you were to pick maybe one side of the market to be drawn from a model more like the one from Clay's paper, is your intuition that that still immediately becomes intractable, or do you think there's hope of that maybe being a good direction, and which side of the market?
That sounds like a great direction to me, because it's, as also Clay mentioned, it's maybe the first step to go beyond uniform distribution. I should think more of like which side of the market to be tiered. Maybe Clay has some ideas.
For our paper, putting the proposing side in tiers was much harder, but it might depend on the exact model. The fact that the like non-sorting fact that we got, we sort of interpreted it that you need something stronger or different than our model to, for example, tell people who they should interview. Since the real stable matching in our model doesn't tell you who should match to who with any significant predictive power, maybe you would need something like polynomial gaps in scores.
All right, and I think there's one more paper-specific question from Aviad that's written down, so I'll just read it out loud. Is Vijay, can you elaborate on what you meant by an extension to two-sided matching?
Oh, yeah. So suppose that you have two sides. So these are not agents and goods being done, but let's say agents and employers, okay, workers and employers, and each side has preferences for the other side, given not through a preference list like in Gel-Shapley, but given through utilities, UIJs and WIJs, okay? And now, you can extend the definitions to get a notion of equilibrium and so on and so forth. Does it exist? What are algorithmic results there? What are irrationality results there, more importantly, because those will be many, many more. Probably, my guess is even 0, 1 is irrational. So I played around with it quite a bit without getting any positive results. And there are, so I've been in touch with Zeckhauser, and the very first time I sent him an email, he sent me this long a list of models that he wanted to attack. And I told him, look, we cannot even do the basic model. How can we go any further? So, so the point is that you can think of many, many interesting models. And he said, this is interesting, and this is interesting, and this is interesting. Yeah, they are interesting, but what can we do? So we are waiting really for some positive news on maybe approximate equilibria or something else before we can head to all those models. And I think the economists and maybe even the applications, people will like them once they get found and worked out. But good question, Aviad. Let's do it next fall together.
Do you think approximation is doable? Or should that be hard?
I have really tried hard. The weak gross substitutability, which is the main stumbling block for exact computation, comes up very strongly in approximate also. Sometimes one can get around weak cross substitutability. People have some results like that, but in this case, it's quite severe. I have some other ideas. Maybe if they pan out by February, March, I will share them with you through some forum or the other.
Thank you.
Cool.
But please be mindful of the age of the authors, because the younger people have to take over the mantle now.
Cool. I just want to give a quick heads up to everyone that it's almost to 11:30, and the next session is going to start in room B. There's still another question, so we'll take the question and we'll keep talking. But if you were hoping to go to the next session, that was just this is your warning that it's going to start soon.
Okay.
So there was a question for Clay in the chat. I'll just read it out loud for the recording. Do you have any thought about how to check empirically your result that every pair of agents has the same probability of being matched property?
So we've checked it with simulations, or rather Geng has checked it with some great simulations. And although the convergence is really slow, it does go to uniform in constant tiers. In real life, I don't know if we could find markets that satisfy these assumptions really well. Preferences are really correlated. You know, even if the gap is pretty big between, say, Harvard and Cambridge Community College, a constant score gap would predict that 1% of people would rank the community college above Harvard. So I would say that this points in the direction that this indicates that you need stronger assumptions to get the sorting that we see in real world markets.
Nice. So I had only prepared kind of like one more general question myself. So I'll just ask, but speakers, you should feel free to just ignore it and drop off if you're done. So I was curious if the speakers or any of the co-authors who are panelists who wanted to share, if you wanted to share, maybe this is more relevant for the students in the audience, what was like the most exciting paper in the research area relevant to what you just presented that kind of like got you really hyped to work in this area, or that got you excited to start whatever project you just presented? Or it could be a series of papers or something. And I guess we can go in any order, and the co-authors who are visible can share too.
So for me, I think it was actually, Matt, when you told me about the Ashlagi Kanoria Leshno result, that with just say n men and n-1 women, the advantage of being the proposing side is basically completely neutralized, and it's better to be a woman because you just have that one fewer agent, and imbalance is really powerful.
So maybe I can go next. So for this literature of online matching, so I think the most inspired paper for me is the KVV's paper in 90s, which introduced this very fundamental model. And so later in the DJK13 paper, they introduced this classic framework of primal dual analysis to analyze this competitive ratio. And even in the recent study for more complicated model, they are also trying to adapt this primal dual analysis. And I think those are all very great paper.
Can I add a comment to your thoughts?
Yes.
So following up on the primal dual analysis, there was exactly based on that, really taking all their ideas. There was a paper of Michael Feldman and Amos Fiat and some other people giving an economics-based analysis, and that's particularly clean. And these two are really, for the first time, textbook quality analysis, because KVV was never in a textbook. And as I mentioned, there's a book on matching markets. In one of the fundamental results chapter, there'll be an exposition of KVV. It will be on my website as soon as I put it there, that chapter. And you can see the very, very, very clean analysis, so beautiful, coming from these two papers. It's finally, you can teach it, I believe, even to undergrads, certainly to graduate students. I'll put it on my webpage. I promise. Today is what, Wednesday? Certainly by next Monday, you will see it on my webpage.
Nice. And for those of you following in the chat, there's also some references to the papers that just got mentioned.
Yeah, talk at SOSA this week. Yeah, that's Kira just mentioned that the Michael Feldman et al. Paper will be in SOSA. Yeah, Alon Eden also, yes. And I believe Amos Fiat, and maybe there's one more author. I forget. Yeah, cannot remember everything anymore.
All right, I guess if no one else wants to share, we can end the session. I guess Hedyeh, do you have anything you want to share?
Sure. For me, it was a Morlika Mahdian paper from 2005 that got me interested in this whole matching market with shortlist, and they're actually like interesting solutions. That's quite interesting for me.
Nice. Okay. So maybe we can end the session, but I think a lot of the authors mentioned that they're happy to follow up offline, and we'll see you all back in Gather. Thanks for joining.